Now we're going to talk about decomposition reactions. And decomposition reactions are essentially just the reverse of synthesis reactions. So in this case, when you are looking for decomposition reactions, you will only ever have one reactant breaking down into many different products. So in this example that I have in this animated GIF here, you've got ammonium dichromate, and it is decomposing into nitrogen gas, water, and this chromium 3 oxide. So here we've got three products, but we only have one reactant. So the general equation is AB will yield A plus B. But note that you can have more than two products at any one time. When we are looking at the scenario where you have a relationship with synthesis reactions, you have person A hooking up with person B, yielding a couple AB. Here is where the couple would now break up and they're back into their individual states. Sometimes it's not as simple as just a compound breaking down into its simpler elements. It might be a larger compound breaking down into simpler molecules. So those would be our special case scenarios that we've seen in the past. So here is a great example of a decomposition reaction of potassium chlorate that I'd like to play for you.
And it's not going to decompose on its own. We need to provide it with some energy, some activation energy. So at the moment, I'm heating it up so that it can melt. And when we've got molten potassium chlorate, we'll almost be ready to do this decomposition reaction. So the potassium chlorate has now melted. We have molten potassium chlorate. There's a lot of thermal energy there, but it's still not going to decompose as quickly as I would like. Even though temperature is one of the major factors for increasing the rate of a chemical reaction, we need to provide a little bit more energy, and I'm going to use Skittles. You could also use gummy bears. That's the traditional way of doing this experiment, but the main component of candy is sugar, C12H22O11. It's a hydrocarbon. When I put a Skittle inside there, it's going to combust, it's going to burn, and that bit of energy is going to initiate the decomposition reaction for the potassium chlorate. I'm going to do it in a moment, and I want you to observe the release of smoke. That smoke is potassium chloride. I want you to hear the rush of oxygen gas escaping. That's why this is used as a rocket fuel. And then I have a question for you. I want you to look closely at the color, and I want you to try identify the metal that is being excited from the energy of this reaction.
So as we could see from that reaction, we had potassium chlorate breaking down into potassium chloride and oxygen gas. Unfortunately, this word equation and balanced chemical equation got cut off here, but you can see in this animated GIF that is exactly what is happening there. And that purple flame that you saw was due to the potassium compound. Okay, potassium often yields a purple type flame. Decomposition reaction, this is also a common demonstration seen on the internet. It's also referred to as elephant's toothpaste. What it is hydrogen peroxide, which you can buy at the drugstore, but the one that you can buy at the drugstore is 3%. You need something that is a little bit stronger, closer to a 30% concentration in order to get the effect. What essentially you do is you put some hydrogen peroxide in a cylinder or graduated cylinder, and you put some liquid detergent, And then what you do is you use a catalyst, something like potassium iodide or yeast. And what will happen is it causes the hydrogen peroxide to decompose rapidly. If not, it's too slow of a reaction. And when it decomposes, it creates water and oxygen gas. The oxygen gas gets trapped within the actual liquid detergent itself. And so that's what causes it to sort of bubble up. If I was to use a glowing splint, I would see that the glowing splint would relight as evidence of the oxygen gas. So this is another decomposition reaction. So decomposition reactions, again, as we stated, are just the opposite of synthesis reactions. In this case, if you had a binary compound, it would break down into its simpler elements. And then when we have our special case scenarios, which we'll see in the actual lesson worksheet, when we have acids, they will break down into non-metal oxides and water, whereas we saw with synthesis reactions, if these two got added together, it would create an acid. So essentially, we're just flipping the equation. In a synthesis reaction, we know that metal oxides in water react to form a metal hydroxide or a base. In this case, the base, which is a metal hydroxide, will break down into its metal oxide in water. And metal carbonates will break down into metal oxides and carbon dioxide. So if you're really comfortable with synthesis, you should be okay with decomposition because we're just flipping the equations. Let's go on to the lesson worksheet.